Today's version of the International Inverse Problem Seminar. So we're happy today to have Barbara Kaltenbacher from Klagenfurt, which will be talking about imaging with nonlinear and fractionally damped waves. Thanks a lot for giving a talk, Barbara.
So thank you very much for having me, and let me take the opportunity to thank you very much indeed for running this seminar series, basically all through this pandemic time, which was really a great thing to have for the inverse problems community. So thank you very much for this. So about the title, actually, to be honest, most of the talk will be on these waves rather than the imaging with waves, but there will be some parts also about inverse problems related to this and how to do images. And talking about images, it's mainly in the context of ultrasound imaging that we think here, because non-linearity and fractional damping, that's typical features that appear in ultrasound and high intensity ultrasound for this non-linear part here, respectively. So a big part of the lecture will be taken up by modeling, or by looking at models and how one gets to these models, or just trying to give an idea on how one gets to these models. And the two inverse topics will be about photoacoustic tomography, which is a linear inverse problem in the presence of fractional damping. And there will be a very short final part about imaging with nonlinear waves, namely recovering what is called the nonlinearity parameter in the nonlinear wave equation modeling high intensity ultrasound. Okay, about nonlinear acoustics, so that's best explained maybe by a picture first of all, before going into equations. So what we have is, so this is a simulation, these are snapshots from a simulation. First of all, you see we have sort of a continuous wave excitation at this left boundary with a basically sinusoidal wave that starts here, and it propagates into the domain. So you here see the cross section, the profile of the wave. And as it proceeds, you see it's steepening up here. So this part here is steepening up as compared to this. And this is getting a bit flatter here as compared to here. And also the amplitude is getting lower. So there's also a bit of damping involved. But the important piece is that really the wave changes its shape. The profile changes its shape. And that's basically, so to say, physically speaking, due to a changing sound speed. So the sound speed depends actually on the state, on the pressure. So here we have high positive pressure values, then it's faster. And here we have high negative pressure values, then it's slower. And that's how we get to these steepening waves. At the end, one really gets what is called a sawteeth profile. So this really zigzag up, down. So, and we will actually see this dependence of the sound speed on the amplitude in the equations later on as well. So how do we get to the wave equation, or more generally to nonlinear wave equations? So it's basically, it results from physical balance laws together with, so to say, material laws. So the important quantities here are the particle velocity, the pressure, and also the mass density. There's further quantities, but for the models that we are going to look here, it's enough to look at these three decisive quantities. All the three of them are functions of space and time. So one has a certain pressure at a certain point in space and a certain time instance. And they also can be decomposed, so to say, in small parts and large parts. So the large parts, or the relatively large parts, are these mean values that are constant in space and time. And then the fluctuations that from which we, so to say, get the sound that we can perceive, that's these small parts, these fluctuating parts that then really depend on x and t. So here are the governing equations. So there's two balance equations, balance of momentum basically, combined with the fact that in our applications the velocity is typically irrotational. We end up with this one here. So maybe you can recognize at least rho times Vt plus gradient of P, that this is sort of a balance of momentum, at least the linear part of it. There's the balance of mass as well. So this is something which might be familiar to some extent. So this is really a balance of mass that is, so to say, transported over space and time, and also changes in time. And then we have so far just two equations for three quantities. So we need something like a material law to close this. And that's the equation of state, as it's called in acoustics. So that's actually the relation between the relative pressure fluctuations in terms of the relative density fluctuations, or vice versa. And actually, in general, that's a nonlinear relation that one has. There are certain formulas that one assumes with ideal gases and so on and so forth. But in general, it's a nonlinear function. And what physicists do is they do a Taylor expansion, which actually they learn very early on during their studies, as I've seen with my daughter. So Taylor expansion is very important here. And you can also see it. So this is sort of the zero order, the first order term, sorry, zero order is just zero, the first order term, and this is the second order term. And there's also a bit of an expansion, not only in terms of the pressure, but also in terms of the entropy. And that's where this time derivative term comes from, just without going into details. There's further physical constants here, this mu bar appearing over here and this mu tilde appearing over here. They basically are sorts of viscosities. So that's why I abbreviated them by mu's, but it's just constant. So these are quantities that don't depend on space. However, this B over 2A, this is something which is actually space dependent. And we will use this later on for imaging. Okay, just to repeat, these are the three balance equations and three equations, two of them balance and one of them this equation of state. And let's have a look at how one gets a second order wave equation from this. And for this purpose, let's just have a look at the linear parts. So as I've already mentioned, this part and this part give the linear balance of momentum. And this part together with this one gives the linear part of the equation of continuity, but just neglecting this, so to say, second order term here. And also from this equation of state, we just take this first order term, and by c square, we abbreviate this fraction here between p0 and ρ0, which plays the physical role of the speed of sound. So c is the speed of sound, and it's related to this mean values of pressure and density. And let's also recall that dependence of x and t respectively only occurs in the fluctuating parts and not in these average parts. So if you take, for example, if we take the divergence, we can just pull out the ρ0 here. So now let's collect what remains. So these are the two linear balance equations. And now we can express this rho by means of this linear equation of state in terms of p, or actually pt, because we have a time derivative here, using the 1 over c square. And what we want to do now is we want to derive just a single second order equation in terms of p. And for this purpose, we want to eliminate the velocity. So it's still there, but that's easy. We just have to take the divergence of the first equation and subtract from the second equation, or vice versa. So subtract from the second equation that we differentiate with respect to t. Then clearly the v parts go away. And what we end up with is, well, we then have a second derivative of p tilde times 1 over c squared. And we have minus divergence of gradient, so minus Laplace p tilde. And that's the well-known linear second order wave equation for the pressure P. Now, in order to derive nonlinear models, we go back to our nonlinear balance laws and also this nonlinear equation of state. And we do basically the same elimination step, namely this one, taking the divergence of the balance of momentum and subtracting it from the time derivative of the equation of continuity. But this will not completely eliminate V. So we have to do a few further skipping steps. And that actually follows a certain scheme, the so-called Blackstock scheme, that tells us which terms we can neglect and which we cannot neglect. And what we end up with is finally second order wave equation. So you see this here. So you have again this part that we had already previously in the linear wave equation, but we have a nonlinear term on the right-hand side. And this nonlinear term comes with this B over A coefficient that we had in modeling, so to say, the relation between rho and P. There's also a damping term, so this B Laplace PT that comes from all these, basically from these viscosity terms. And there's also still a leftover V here. There's a leftover V squared norm term here. So the V can actually be related to P, not V itself, but actually its time derivative because of this, that's just the linearized momentum balance. And that's one of the rules of these elimination rules in the Blackstock scheme, that if it comes in a higher order term, here it's a second order term, we can replace a quantity by its, so to say, by its linearized equation. And so that's the substitution corollary. And so we can substitute like this. Well, still we don't like to have this vectorial quantity because actually we would still have to consider these two equations here, one for the V and one for the P, or both of them coupled for V and P. But what we can do is use the fact that V is irrotational and therefore it's the gradient of a potential. And so it's actually usually physicists and engineers like to write it as a minus the gradient of a potential. And doing this, no, I didn't want to do this yet. So this term clearly becomes the gradient of this psi. And also P can be expressed in terms of psi. Because if you look at this equality here, then we have gradient of P over here. And then here over here, we have the gradient of psi T. And if we sort of, so to say, we skip the gradients, we see that P is just equal to rho 0 times psi T. Plugging this in over here, we get terms in, we can replace P terms by psi terms. And we also integrate once with respect to T in order to remove one time derivative here and in order to really get from P to psi. Okay, that's the Kuznetsov equation. That's the classical model of nonlinear acoustics. And the simplification arises if we do a different approach to remove this V term, namely by approximating it again by some sort of linearized version. So basically just taking into account, not taking into account local nonlinear effects. So we can make this approximation here and everything then can be written in terms of P. That's the Westerveld equation. Okay, here we have this nonlinearity parameter in either of these equations, and it will play a role later on as well. So what's interesting mathematically about this Westerveld equation is the fact that second time derivatives also appear on the right-hand side. And so if we move this term over to the other side, we get this expression here. And so we have sort of a nonlinear expression of u under the second time derivative, which makes it also sort of challenging, because if this term here loses its correct sign, then we are in trouble. Or if it becomes 0, then the equation just simply degenerates. So we have to avoid this. And on top of this, it also illustrates this state dependence of the effective wave speed, because we can just differentiate this out, the second derivative, and then we can just rearrange terms. Then we can write this equivalently as such an equation here, where instead of the c square, we have a c tilde square. So after differentiating out, we get 1 plus 2 times kappa times u utt. We divide by this 1 minus 2 times kappa times u, and that's how we get, after taking the square root, how we get this c tilde. Likewise, also b becomes a b tilde, and also we get the right-hand side term here, which is also not nonlinear. But the crucial thing is here, we are dividing. So first of all, we are taking the square root of this thing here, which is only makes sense if the object under the square root is positive, if we want to have real valued solutions, because also we divide by the square root. And so it's really important that we keep u not too large so that this quantity doesn't degenerate. And it also illustrates that the effective speed of sound, this c tilde, depends on u. And so if u gets larger, then the denominator gets smaller so that the overall object becomes larger again, sorry. And the other way around, if u is negative, then this becomes larger, and so the sound speed gets smaller effectively. And that's the explanation for this sawteeth profile. Okay, so that this was about nonlinearity modeling. Now about fractional damping modeling. So it's especially important in ultrasonics because just phenomenologically, one observes that in ultrasound propagating in tissue, one has dependence of the sounds of the damping actually on the frequency, namely on powers of the frequency, fractional powers of the frequency. And if one goes from frequency domain to time domain, these fractional powers become fractional derivatives. And that's why one uses fractional derivatives there. So in order to introduce fractional models in acoustics, I start first of all, so to say, historically with fractional models for in elasticity. Actually, it's linear elasticity. Which was the first motivation for doing that. Actually, it was Michele Caputo, one of the reinventors of fractional derivatives, who looked at this. So in viscoelasticity, we have balance equations, namely the equation of motion that resides from a force balance here. So U is the displacement, sigma is the stress, and F is some volume force that might be an exciting force here. And on the other hand, well, it's not really a balance equation, but it's just simply a relation between the strain and the displacement. That's the linearized one, where we write the strain as the symmetric gradient of the displacement. So in full, it would still be a nonlinear term over here, but we skip that. So that's, so to say, geometrically linear elasticity that we do here. And on top of this, we need a constitutive model that relates the strain epsilon with the stress sigma. So to close it, and then everything can be written in terms of the displacements. So this constitutive model is in pure elasticity, it's just Hooke's law, where the stress is proportional to the strain. But if one goes to viscoelasticity, it might also be that this stress is not proportional to the strain itself, but to the strain rate, so time derivative of the strain, or to a combination of strain and strain rate, or the other way around, stress and stress rate are related to the strain, or even more generally, the combinations, the combination of stress and stress rate is equal to a combination of strain and strain rate. That's the most general de Siena model here. So we can do similar things on a fractional level, just taking the fractional derivatives of these rates instead of the integer first order derivatives. So all these dt beta or dt alpha, these are now fractional derivatives. I will say in a moment what this is. And in order to derive wave equations from this, usually one just goes to one space dimension where also these displacements, stresses, and strains have just one component. So one can even most generally take arbitrary fractional linear combinations of several fractional derivatives of sigma on the left-hand side and several fractional derivatives of epsilon on the right-hand side. Now let's do this for acoustics. And for this purpose, let's recall our balance laws, balance of momentum and balance of mass. And now just looking at the linearized ones, plus some excitation force or excitation moment actually here. And we also just look at the linear equation of state for the moment. So actually this equation, linear equation of state, corresponds to what is Hooke's law in elasticity. It's just a linear relation between the governing quantities. And we could, analogously to elasticity, we can replace this linear relation that just involves zero derivatives, like in Hooke's law, by a linear combination of fractional derivatives on both sides. And actually plugging this into this balance of mass and balance of momentum, and also doing this elimination step of subtracting the divergence of the balance of momentum from the time derivative of the balance of mass, we end up with second order wave equations for the pressure P. So again, you see these parts where it's just a second order wave equation in terms of P. At least you still see it here. You can also see it in parts here. But there's also other terms, and these are typically play the role of damping terms. And that's what actually is desired in order to model this power law frequency dependence of the damping in ultrasonics. It can actually also affect the time derivative, so that we can even end up with an equation that has a leading order time derivative that is larger than 2. So these alphas and betas will always be somewhere between 0 and 1. We also have this possible combination here of both things, or even this most general one, also in acoustics. Okay, what are these fractional derivatives? So fractional derivatives are typically defined, at least these one-dimensional fractional derivatives. Of course, you are certainly aware as a follower of this lecture series that there's also the fractional version of the Laplace operator, but that's not what we are looking at here. We are just looking at one-dimensional fractional derivatives, and there they can be very nicely and conveniently and also mathematically rigorously defined as by first of all taking fractional integrals. And so the classically fractional integral operator is due to Abel. It's also called the Abel fractional integral operator. So in those problems, people sometimes know it from a very special case of the radon transform, which also leads to an Abel fractional integral operator of second order. So with gamma equal to 2 here. That's what one sometimes shows in those problems lectures. But this is the general Abel fractional integral operator, and you see it's really a scale of so to say powers of the integer order derivative. If we put gamma to 1 here, yes, gamma is equal to 1 here, then it's just the classical integral operator, because then its denominator is just 1, so the exponent is 0. Then it's just integration of f, just taking the antiderivative. But a particular antiderivative, namely the one starting at the point A. And it's also, well, integration involves all values between A and T. So that's also, as a consequence, the fractional differential operators will be non-local in time. So now, in order to get a fractional derivative, what we do is we apply a time derivative, just an integer time derivative. We have two choices. We can either do so before applying the integral operator or after applying the integral operator. So the former is, well, maybe more general because it needs less assumptions before doing that integral of f is certainly feasible for a larger function class. because only afterwards we do the differentiation. But this second option is actually more convenient for modeling physical phenomena by means of initial value problems, because it admits imposing initial values. So for this, as it's called, Riemann-Liouville derivative, actually one has a singularity at 0, and so it's really problematic to prescribe initial values for functions for which we impose an ODE using the Riemann-Liouville derivative, unless this initial value is just 0. So this Djabashan-Caputo derivative is the one that is mostly used when doing PDE models, and namely time-dependent PDE models where one prescribes initial values. Okay, it's so to say with this integer first order derivatives cancels, so to say, part of this integral, and what remains, so to say, is an integral of the order minus alpha, which is then a derivative of order plus alpha. So I already pointed to this non-local character of the fractional derivative, because it involves values over the whole interval from a to t, not only at the time instance t. And as a consequence of this, there's also a certain memory effect in the PDEs involving fractional derivatives. And in particular, if one wants to go backwards in time, like, for example, in the classical backwards diffusion problem, then one is much better off if one just has a fractional time derivative rather than the first order time derivative that one usually has in the heat equation. And that's also to some extent due to this memory effect over the whole time interval. So I'm not going to talk about backwards heat, but I'm actually photoacoustic tomography is related to this. It's also to some extent going backwards in time. And so next I would like to look at the inverse problem of photoacoustic tomography with fractional attenuation. So this is motivated by the fact, as I already said, that fractional attenuation happens really in ultrasound in human tissue. And so just to recall, this photoacoustic tomography, it's actually a subproblem of the overall problem of photoacoustic tomography, but the acoustic subproblem of it is to reconstruct an initial pressure from observations of pressure over time, over the whole time interval, and this way also, so to say, looking backwards in time. And therefore, these fractional time derivatives in the sense of having these memory effects also play a certain role for that inverse problem. So it's known that if we have no attenuation in photoacoustic tomography, then the problem is basically well posed, or it's almost well posed, it's only mildly ill posed. So there's a bit of a derivative loss in regularity, but just finite derivative loss, and that's due to the fact that wave propagation really happens losslessly if we have no damping. However, if damping occurs, and it does occur, then we have to expect there will be more ill-posedness, and especially if we take strong damping, so first order. So if the, for example, in that model here, the beta is a first order derivative. That's the classical Kelvin-Voigt damping, the integer one. Then it's known that the problem becomes severely ill-posed, because actually, if you have this strong damping here, the equation behaves like a parabolic equation. And that's, so to say, closing the circle to the backwards heat problem somehow. Okay, the question is now, how is it? So we know with first order damping, it's severely ill-posed. Without damping, it's mildly ill-posed. So what happens with in-between damping, so with fractional damping? And indeed, we will see that with fractional damping, the behavior is really in between. And so the stronger the fractional damping is, the higher that fractional index is, the closer we are to this severe ill-posedness. And the lower it is, the more mild the ill-posedness becomes. Okay. So there's also something about uniqueness, which I will, I think, more or less skip here. Let me just shortly mention it a bit. So the inverse problems that we look at here is as follows. So we have a wave equation with this operator A being the negative Laplacian here, and D being one of these damping operators that we had in the fractional damping models. The initial value is what we want to recover. So U plays the role of the pressure here, and we want to recover the initial pressure. We assume that the time derivative is just 0 at the beginning. And so that's what one has to assume actually here. And the observation that we have is an observation on on a surface inside the domain omega. So this sigma is, and if omega is d-dimensional, then sigma is a manifold of dimension d-1. It models an array of transducers where we can measure the pressure. So actually, a completely realistic model might be that we just have points actually. So sigma just consists of points, but it's a really good approximation to look at sigma as something like an n-1 or d-1 dimensional manifold. And just to say what these damping terms here, they are the damping terms that you have seen in the derivation on one of the previous slides. So we are going to consider 3 of them: this Caputo-Wismar-Kelvin damping model, where we have a time derivative, a fractional time derivative. The fractional Zener model, where you have this combination of time derivatives, one going higher than second order, and one being combined with the negative Laplacian here. And there's another one which I want to mention here, which is a space fractional one. So where we take a power of the Laplacian, and that's then really a version of the fractional Laplacian, namely the spectral one. So we can combine these. We can combine these 2 of them by putting a beta tilde up here and keeping this beta here. So to a Caputo-Wismar chainhole model, to abbreviate it, we just take C and H, so the very first and the very last capital letter, and fractional Zener will be abbreviated by FZ. Okay. Also, in order to get well-posedness of the forward problem, we need to impose certain conditions on these coefficients here. That's just basically stability conditions in order to have to guarantee that the solution not only exists but also behaves in a stable manner. And then, just to quote the uniqueness result, what we were able to show is that under a certain condition that basically states that we have enough information on our observation surface sigma, we can reconstruct our initial condition U0, our initial pressure. Okay, what does it mean more precisely? Well, the proof of all this is based on a spectral decomposition of the operator A on our negative Laplacian. And correspondingly, what we can do is to do a separation of variables representation of the PDE solution in terms of a series expansion, in terms of the eigenfunctions of the Laplace operator. And what we do is now to collect all the eigenfunctions that correspond to the same eigenvalue lambda in a finite set. So it's known that this is it's always a finite set, but it can be several of them. So what we can prove in the first step of the proof is that really we can disentangle the contributions coming from different eigenvalues. That's because we can look at poles of our measurements, and the poles allow us really to distinguish between different eigenvalues. Actually, what we can do is really also to even reconstruct the eigenvalues of that operator A. But if these eigenvalues are not single, then there are several eigenfunctions. There might be several eigenfunctions. In higher space dimensions, that's true. In one space dimensions, there's only just one. But in higher space dimensions, there can be several eigenfunctions. And in order to disentangle the information coming from these several or pertaining to these several eigenfunctions, we have to assume the following. We have to assume that when restricting the eigenfunctions to our observation surface sigma, these functions that are functions of the points on sigma, then these functions are linearly independent. That's what this condition says. And under this linear independence condition, one can prove uniqueness. So there are key ideas of the proof. Let's just skip these remarks. The key ideas are that one can do separation of variables. Well, I wanted to put this one, sorry. One can do separation of variables here in the solution representation and also in the representation of the observations. Then doing analysis in Laplace domain, so Laplace transforming everything, one can look at the poles of the Laplace transforms, and from these poles, one can obtain the eigenvalues, and from the eigenvalues, one can obtain the crucial spectral information on U0 in order to separate the information within each, so to say, within each eigenspace corresponding to the same eigenvalue. We need this linear independence condition. Okay, was there a question or is it just okay? Okay, so sorry, I don't have time to give you the proof, because I would like to say something. I would also like to illustrate a bit how this dependence on the fractional order of the damping is. So, and this is done here with this fractional chainhole model, where we have both space fractional and time fractional component. So we looked at variations of these both betas, beta tilde and beta. So here these different pictures, top and bottom, correspond to a, so to say, medium to small value of this beta here. So we have, so to say, weak damping with respect to the time derivative. And here we have strong, relatively strong. So it's almost 1. So we are close to the strong damping paradigm. And this can be seen by the position of the poles. So the poles move away from the imaginary axis. The further away, so the weaker the damping, the closer we are to the imaginary axis. And also the beta tilde plays a role, because if beta tilde is 1, here again we are in the strong damping regime, here and here. If beta tilde is small, we are also close to a weak damping and we are close to the imaginary axis. So why does this mean almost well-postness? Well, because basically it's inverting Laplace transforms. And if we have the Laplace transform on the imaginary axis, it's a Fourier transform, and the Fourier transform can be inverted stably. So that's, so to say, the intuitive argument behind that. Here is also the influence of the speed of sound. So if the speed of sound is larger, here it's just 1, here it is 5, then also the damping effect is less pronounced as compared to the wave propagation effect. And then this way also you see from the scale here actually that one can recover also larger components, so higher frequency components in the spectrum. Okay, just to give you an impression about reconstructions. No, I have no time for showing this. And anyway, it's just 1D reconstructions. So maybe that's not what you typically call imaging. It's just 1D images. Okay, but you see, again, you see the influence of the damping. If the damping is stronger, then with noisy data, one has a harder time recovering the exact thing, which is the dashed and actually also the red value, which one obtains quite well with low damping here, even with a larger noise level. So this is the larger noise level, sorry. Okay, now let's move on in the last few seconds to nonlinearity parameter imaging. And here I just want you to give an idea on what it's all about. So recall we had our Westerveld equation. Now we are back to a nonlinear regime where the coefficient kappa, which contained this B over A nonlinearity parameter, appears. And it's actually a function of x, because nonlinearity is it depends on the type of tissue. It not only depends on the type of tissue, it also depends on whether we have contrast agents here. So people are injecting, for example, microbubbles. And where in the presence of these microbubbles, there's also a more strongly pronounced nonlinear effect than outside. So this kappa of X is really something which one can use for imaging. And so kappa of X is the function that we want to reconstruct in order to get, so to say, an image from the interior of the body. So the measurements are, again, basically these surface measurements at the transducer array over time. And so first of all, the question arises, is it at all possible to reconstruct kappa? And how ill-posed is the problem of reconstructing kappa? So the answer is it will have a tendency of being very ill-posed because we are measuring basically in time direction. But we want to reconstructing something which is, so to say, in the orthogonal direction, in X direction, and that's known to be severely ill-posed. So just to mention what the D is, again, we have our three possible damping models here. So it's not only nonlinearity, but it's also fractional damping that we have here. And just to wrap up what the challenges are here, first of all, the forward problem is already nonlinear, and the nonlinearity occurs in the highest order term. And on top of this, the search for quantity in our inverse problem appears in that nonlinear term. This is a challenge for doing analysis, but it's also an advantage because sitting in this nonlinear term, and this actually reminds me of a very nice talk of Katja that she has given at RICAM. Nonlinearity actually makes it easier to reconstruct things. And actually the fact that kappa, the thing that we want to reconstruct, appears in that nonlinear term, that from the inverse problem point of view, it makes it easier. That's the thing that I already mentioned, that kappa is spatially varying, the data is time varying, and so we have to expect severe ill-posedness of the inverse problem. But so the fine degree of ill-posedness will again depend on the damping that we have. So just to also mention what we have done so far, we have analyzed the forward problem and proven well-definedness of the forward operator that maps the kappa into our observations. It's also Fréchet differentiable, so we can apply Newton's method, and we can really apply Newton's method because we also have linearized injectivity, at least at kappa equal to 0, so we can apply a frozen Newton method at kappa equal to 0 in order to recover a non-zero kappa. Okay, so that's what we obtained. These are the reconstruction, again, just 1D, that we obtained by our frozen Newton method. And what I want to illustrate by this is, again, the influence of the strength of the damping. So here it's just this Kauputo-Wismar-Kelvin damping with just one, so to say, damping parameter beta. And again, the closer we are to 1, so if beta is 1, then we are again in this severely ill-posed regime. And if beta is smaller than 1, we get closer to a wave type regime where if information is processed in a more or less almost lossless way. And one can see this by the fact that reconstructions are actually much better than. This is with really relatively small noise. With a bit larger noise, 1%, it's even more pronounced, as you can see here. Okay, it can be also read off by the singular values of the linearized forward operator. So ill-posedness can be quantified in terms of the decay of these singular values. The faster they decay, the more ill-posed the problem is. And here you see it's actually log scale. So the larger the beta is, the stronger the damping is, the faster these decay. And again, if there's a higher wave speed, so if the wave propagation is more pronounced, then this gets, so to say, it gets ameliorated to some extent, so it gets relativated. So with this, let me thank you very much for your attention. And of course, I'm happy to answer questions.
Great, thanks a lot for a very nice talk, Barbara. So yeah, if you have questions, please feel free to unmute yourself and ask questions. So I was wondering a little bit, but you mentioned that these fractional time derivatives, they are relevant for tissue modeling. Was that so? To model propagation in tissue.
Yes, it was actually for modeling the attenuation in tissue.
Yeah. So, but you have several models. So, is there sort of a consensus about what's the better model? Is it this fractional chainhole model that is sort of the best one, or so? What is sort of the recommendation regarding tissue?
So, no, I would not dare to give you a recommendation here. So, this is something which one has to ask the physicists.
Yeah.
So, I think, according to to what I read from the literature, my impression is that they are also not decided about this yet. So of course, there's always the compromise between simplicity of the model and whether it all captures all effects. And they seem to be still debating among themselves what the right compromise is, so to say. And on top of this, in our case, we also have to do, so to say, the additional criterion is what is best for our inverse problem, so to say. And so with which model we can solve it most efficiently and most reliably, but still keeping physics in mind.
Right, yeah.
Yes, Matthias, you are?
Yes. Hi, Barbara. Thank you for your talk. Very interesting. Here, I have a question. I think I missed the point there when you had this theorem about the uniqueness in the photoacoustic tomography, the condition on linear independence.
Yes.
Is there also a condition that the observation surface is closed?
Well, there's this well-known condition for photoacoustic tomography, which is satisfied if the observation surface is closed and the sound speed, if it varies with time, with space, which is it can here actually. I'm exactly on this slide where I mentioned it can depend on space, but if it depends on space, then in that meanwhile sort of classical result, it needs to satisfy a non-trapping condition. So this is now sort of combined, so to say, in that linear independence condition. So it's also, well, what one can do on the positive side, what we can do is in certain geometries where we know the eigenfunctions are separable, we can show that if the observation surface is a closed surface, so for example, if we have bowls or something like this, that if the observation surface is also a bowl, a concentric bowl with a radius that should not be a rational number, actually, then because of the special form of the eigenfunctions as Henkel functions, and then we have zeros of these Henkel functions. But if this is satisfied, then such a closed observation surface actually leads to this linear independence condition. So we do have examples where this linear independence condition can be related to that, so to say, classical condition, closed surface and non-trapping. But that's actually an interesting question that we want to further explore, is really how this, so to say, proof driven, and if I could have shown you the proof you would have seen why this condition is proof-driven, how it relates to that well-known condition that we have in case of no damping for photoacoustic tomography.
Okay, thank you. All right, so you need just this, and basically, and you have examples where it works well.
Yes, we have examples where these conditions coincide, but we don't know yet which of the two is the stronger one. So my suspicion is probably ours is the stronger one, because it conveniently pops up in the proof. But yes, it still needs to be investigated.
Yeah, that means also basically your solution is not just solving the Cauchy-Dirichlet problem backwards then.
No. It's sort of a different approach.
Yeah. Okay. Thank you.
Mm-hmm.
So any other questions for Barbara? So I was wondering a little bit for the boundary conditions with the fractional time derivative, how does it did it reflect in the boundary conditions again?
I did not say anything about the boundary conditions.
Right. Yeah, but if you
yes, I just glazed over this more or less elegantly, roughly. So so here it's just homogeneous Dirichlet boundary conditions, which of course in practical computations one should not do. And actually, this is just to say what possible boundary conditions could be for which the framework works. But of course, in practice, if one either this domain omega should be all of R3, or one should take absorbing boundary conditions in order to not get artificial spurious reflections from these boundaries. So the more realistic setting would be to have absorbing boundary conditions. However, they then mix space and time derivatives, and this makes the analysis a bit more complicated.
Very good. So very nice, interesting physics and maths. So thank you again for a nice talk, Barbara.
So thank you very much for having me, and also thanks to the audience for coming.
Yeah.
And hope very much to see you soon in person. I've seen there's one person